As people began to better understand the world and universe around them, science and technology began to develop at an accelerating rate. Incredible discoveries and achievements were made all over the globe. One such invention is an item we all know and use quite often: dice. Dice, small throwable objects, are employed in various games to generate random values. Traditional dice are cube-shaped, featuring 6 faces, each marked with 1 to 6 dots or pips. Dice variations include different shapes such as polyhedral, faces marked with symbols or numerals, and numbers carved directly into the material. Dice use extends beyond recorded history, with their origin theories linked to fortune-telling practices using animal talus or knuckle bones. Ancient Egyptians used a primitive form of dice in the game of senet. The oldest known dice were found at an archaeological site in Iran. Ancient Indian texts and the Bible contain references to dice games, highlighting their historical prevalence. Romans, despite gambling prohibitions, were enthusiastic dice players. Roman dice were of 2 sizes, one variant displaying numbers on 4 sides. The existence of 20-sided dice dates back to Ptolemaic Egypt in the 2nd century BCE. In Japan, dice were integral to Sugoroku, a popular game with 2 versions: Ban Sugoroku, similar to backgammon, and E-Sugoroku, a racing game. At around this same time, a far more utilitarian tool was first implemented. It became integral in societies and was used for thousands of years, sometimes still today: the sundial. A sundial is a time-telling device that uses the position of the sun to cast a shadow or light spot on a reference scale. Sundials have been invented independently in every major culture, becoming more precise and sophisticated over time. Prior to the advent of clocks and railways, sundials were the primary timekeeping devices used by governments and commercial entities alike. Even after clocks were invented, sundials retained their importance, as early clocks were not very accurate and needed to be reset frequently using sundials. Sundials became an academic interest in the late 19th century, and today they're largely ornamental, but also studied in some national school curriculums. The earliest known sundials were discovered in ancient Egypt and ancient Babylon. Ancient analematic sundials from the same era were found in modern Russia. Although obelisks were originally thought to serve as sundials, they are now believed to be memorials. Around 700 BCE, the Old Testament describes a sundial, possibly of Egyptian or Babylonian design. Sundials were also used in Kush and China. The Chinese developed a form of sundials around 800 BCE, which later evolved into sophisticated water clocks. The ancient Greeks and Romans made significant contributions to sundial development. Greek sundials, introduced around 560 BCE, derived from their Babylonian counterparts. The Greeks utilized their knowledge of geometry, particularly conic sections, to advance sundial design. Theodosius of Bithynia invented a universal sundial that could be used anywhere on Earth. The Romans adopted Greek sundials, and by 293 BCE, sundials were common in Rome. Vitruvius, a Roman author, listed all known types of dials and their Greek inventors. They all were nodus-type sundials, varying mainly in the surface, receiving the shadow of the nodus. Tools weren't the only important innovations at this time. As we learned more about our bodies and how they work, we began developing some forms of medical technology. One of the most important of these is the suture. Sutures are a type of medical device used to hold body tissues together after an injury or surgery. Their use is fundamental in wound healing by facilitating the joining of tissues, minimizing scar formation, and reducing the risk of infection. Over the centuries, suture materials have evolved significantly, ranging from plant materials like flax, hemp, and cotton, to animal materials such as hair, tendons, arteries, and silk. Early suture reports date back to ancient Egypt, with detailed descriptions of wound sutures from the Indian physician Sushruta in 500 BCE. Notable historical figures like Hippocrates, Aulus Cornelius Celsus, and Galen also described suture techniques, with Galen detailing the use of surgical gut or catgut sutures in the 2nd century. In the 10th century, Abulcasis utilized catgut suture and surgery needle in operations. However, these often led to infections due to insufficient sterilization. In the 19th century, Joseph Lister advocated for routine sterilization of all suture threads, leading to the development of sterile catgut in 1906. The 20th century witnessed a significant advancement in suture materials with the rise of the chemical industry. The first synthetic thread emerged in the 1930s, followed by the production of numerous absorbable and non-absorbable synthetics. Today, most sutures are made from synthetic polymer fibers. Silk and gut sutures remain from ancient times, although the latter has been banned in Europe and Japan due to health concerns. So far, our topics have touched several civilizations, but ancient Egypt has been included in all of them. The next innovation is probably the most thought of when one considers Egypt, the Great Pyramid of Giza. The Great Pyramid of Giza, the largest Egyptian pyramid, was constructed as the tomb of Pharaoh Khufu during the 4th dynasty of the Old Kingdom in the early 26th century BCE. The pyramid, which took about 27 years to build, is the oldest and the only largely intact of the 7 wonders of the ancient world. Part of the UNESCO World Heritage Site. Memphis and its necropolis, the Great Pyramid is the most famous monument of the Giza Pyramid Complex. Originally standing at 146.6 meters, the Great Pyramid remained the tallest man-made structure for over 3,800 years. Removal of most of its smooth white limestone casing reduced its height to the current 138.5 meters. It is made up of an estimated 2.3 million large blocks, amounting to a total weight of 6 million tons. The blocks, predominantly local limestone from the Giza Plateau, are not uniform in size or shape. Imported blocks included white limestone from Tura for the casing, and granite blocks from Aswan for the King's Chamber. The pyramid houses 3 known chambers, the unfinished lowest chamber cut into the bedrock, and the Queen's Chamber and King's Chamber within the pyramid structure. The pyramid was part of a funerary complex that included 2 mortuary temples, tombs for Khufu's immediate family and court, 3 smaller pyramids for Khufu's wives, a smaller satellite pyramid, and 5 buried solar barges. The attribution of the Great Pyramid to Khufu is primarily based on historical records, including those of authors of classical antiquity like Herodotus and Diodorus Siculus. Further evidence came to light in 1837 when 4 additional relieving chambers were found above the king's chamber. These chambers contained red-painted hieroglyphs, including the pharaoh's name, strengthening the pyramid's association with Khufu. Excavations throughout the 20th century revealed cemeteries next to the pyramid where family members and high officials of Khufu were buried, further corroborating its connection to Khufu. The age of the Great Pyramid, estimated to be about 4,600 years old, is determined indirectly through its attribution to Khufu and his chronological age, and directly through radiocarbon dating of organic material in the pyramid's mortar. The majority of recent chronological estimates place the construction of the Great Pyramid within Khufu's reign. This magnificent structure is a testament to the architectural brilliance of the ancient Egyptians and remains a significant archaeological and historical site today. The ancient Egyptians weren't only interested in building amazing structures, at the same time they were looking to the sky to learn more about our place in the universe. Egyptian astronomy, tracing back to the pre-dynastic period, played a significant role in the religious, cultural, and scientific aspects of ancient Egyptian society. As early as the 5th millennium BCE, stone circles at Nabta Playa potentially used astronomical alignments. By the start of the historical dynastic period in the 3rd millennium BCE, a 365-day calendar was established based on stellar observations, particularly for predicting the annual flooding of the Nile. The precise alignment of the Egyptian pyramids towards the pole star, notably Thuban in the Draco constellation due to the precession of the equinoxes, and the temple of Amun-Re at Karnak towards the midwinter sun's rising, highlight the technical prowess of the ancient Egyptians. These orientations underscore the significance of astronomy in religious rituals, timekeeping, and calendrical affairs, including the determination of festival dates. Egyptian astronomy merged with Greek and Babylonian traditions, transforming Alexandria into a major hub of scientific activity in the Hellenistic world. Ptolemy, a notable astronomer from Roman Egypt, authored the Almagest, which profoundly influenced Western astronomy. Following the Muslim conquest, Islamic astronomy and Arabic culture became prominent in the region. Astronomer Ibn Yunus conducted extensive solar observations using a large astrolabe, while Ali ibn Ridwan left a detailed description of the SN 1006 supernova, the brightest stellar event in recorded history. In the 14th century, Najm al-Din al-Misri invented and described over 100 scientific and astronomical instruments. Ancient Egyptians believed in a celestial connection with their rulers, viewing the death of a king as a soul's ascension to become a star. They meticulously tracked the movements and phases of celestial bodies, with the rising of Sirius marking the onset of the Nile's inundation, a critical event in their calendar. Fundamental Egyptian astronomical texts, such as the Book of Nut, reveal the depth of this astral cultural heritage. Pyramids weren't the only amazing structures being built during this period. Central to many of these structures was a simple building concept, the truss. A truss, an engineering marvel typically crafted from straight pieces of metal or timber, creates a series of triangles in a single plane, resulting in a stable structure capable of supporting significant external load over a vast span. It comprises of several components, top and bottom chords, truss joints or panel points, and the web of the truss, consisting of sloping and vertical pieces connecting the chords. Trusses have a historical usage dating back to the early Bronze Age, in primitive lake dwellings. The ancient Greeks utilized trusses extensively for roofing. In the European Middle Ages, trusses were prevalent in various construction activities. Andrea Palladio's 1570 work, 4 books on architecture, included timber truss designs. The advent of covered bridges in the United States during the early 19th century provided a significant boost to truss design. Initially crafted from cast iron and wrought iron, truss bridges evolved to steel construction for railroad bridges. 2 prominent systems, the Pratt and the Warren, differ in their sloping web member orientations. Trusses have extended their utility beyond architectural structures. They are integral to machinery such as cranes and lifts, as well as in aircraft wings and fuselages, underlining their versatile applications in engineering and construction. While we have thus far focused on the Eastern Hemisphere, our next topic takes us west. Living in some of the harshest conditions imaginable, the Inuit people developed some incredible technology to aid in their ability to flourish. The Inuit people, native inhabitants of the Arctic regions of Canada, Greenland, and Alaska, developed a remarkable array of tools that aided their survival in the harsh Arctic environment, particularly for hunting, cooking, and skinning of animals. Key hunting tools included spears, harpoons, arrows, bows, knives, traps, nets, and hooks. These were primarily crafted from bone or walrus ivory, and, when available, driftwood and stone. The spear used for hunting sea mammals like seals and whales was made from a driftwood or bone shaft with a projectile point of stone, bone, or ivory. It was thrown by hand or using atlatls, devices to enhance velocity. Harpoons, useful during annual whaling expeditions, featured a detachable bone or ivory tip and a rope to allow the hunted animal to move and tire out. Bows and arrows, crafted similarly but smaller and thinner, were used for hunting caribou and smaller land mammals. Hunting strategies often involved 2 groups, one to herd the prey closer to the water and the other group waiting in kayaks to kill the animals with bows and arrows. For fishing, the Inuit used traps, nets, and hooks, with ingenious natural traps leveraging tidal changes. Hooks were typically made from ivory or bone, while nets were made from animal products like hide, hair, sinew, or intestines. The 3-pronged spear was another essential fishing tool. Processing and cooking tools included the pump drill, ulu, and kudlik. The pump drill, used for creating fires and drilling into bone or ivory, was critical for tool creation and food preparation. The Inuit often ate raw meat due to the scarcity of fire-sustaining resources. The ulu, mainly used by women, was essential for processing furs and skins. The kudlik, an oil lamp fueled by whale or seal oil, provided light and warmth in their homes. These tools embody the remarkable adaptation and resourcefulness of the Inuit people to their challenging Arctic environment. We have discussed the truss, but the next engineering wonder is much more well known when studying the ancient world and is in many ways iconic: the arch. An arch is a curved structure capable of spanning a space while supporting significant weight. Arches, particularly true arches, were known by civilizations in the ancient Near East, such as the Levant. Their use was infrequent and mainly confined to underground structures like drains. One of the earliest examples is the Nippur Arch, and a few exceptions include arched home doorways in Tel Taya, Iraq, and Bronze Age city gates in Ashkelon and Tel Dan, both in modern-day Israel. In Persia, the Achaemenid Empire built small barrel vaults known as iwan, which evolved into massive structures in the subsequent Parthian Empire. The Greeks introduced the voussoir arch in the 4th century BCE Rhodes footbridge. The ancient Romans, having learned the arch from the Etruscans, refined it and became the first in Europe to fully exploit its potential for above-ground constructions, using it in bridges, aqueducts, and gates. They also pioneered the segmental arch, evident in structures such as Alcanitar Bridge or Ponte San Lorenzo. Despite most of ancient China's architecture being wooden, stone arch bridges are known from this era. The oldest stone arch bridge globally is the Archidiko Bridge in Greece. China's oldest surviving stone arch bridge is the Anji Bridge, while Rome's oldest surviving stone arch bridge is Pons Fabricius, constructed in 62 BCE. The pointed Gothic arch, stronger than the semicircular one, first emerged in the Greek fortifications of Gela in Sicily. The earliest examples of this arch in European architecture date back to the Arab-Norman period in Sicily. The horseshoe arch with its lower ends extended further round the circle until they start to converge, first appeared in the kingdom of Aksum in the 3rd to 4th century, roughly the same time as the earliest examples in Roman Syria. In India, the vaulted roof of an early Harappan burial chamber, the Bittargan Temple and Mahabodhi Temple, are the earliest surviving examples of the voussoir arch vault system. Corbel arches were found worldwide, with an ancient example found underneath the Pyramid of Quetzalcoatl in the city of Teotihuacan, north of Mexico City. We now turn to ancient Egypt once more to discuss an innovation that has been instrumental in the transference of knowledge: papyrus. Papyrus is a thick paper-like material used in ancient times as a writing surface. Produced from the pith of the papyrus plant, Cyperus papyrus, this material also lends its name to documents written on sheets of it, joined side by side and rolled into scrolls, forming early books. Papyrus use dates back to Egypt's first dynasty, benefiting from the abundance of papyrus plants across the Nile Delta. It was employed in the Mediterranean region and used for various purposes, including constructing reed boats, mats, rope, sandals, and baskets. The earliest archaeological evidence of papyrus was found in 2012 and 2013 at Wadi al-Jarf, an ancient Egyptian harbor. These documents, the Diary of Merer, describe the final years of the Great Pyramid of Giza's construction. Later on, papyrus faced competition from parchment, prepared from animal skins. Early Christian writers adopted parchment to form codices, gradually replacing the papyrus scroll. While papyrus was relatively cheap and easy to produce, it was fragile and susceptible to moisture and dryness. The writing surface was often irregular, and the media that could be used was limited. Papyrus was eventually replaced by parchment and vellum in Europe, which were cheaper, locally produced, and more durable in moist climates. The peoples of this time continued to make useful materials using the natural resources around them. While papyrus helped in the spread and perpetuation of knowledge, another material aided in constructing solid, long-lasting structures: concrete. Concrete is a construction material composed of cement, fine and coarse aggregates mixed with water, which hardens or cures into a durable stone-like material. The use of concrete-like materials dates back to ancient times. The Nabatean traders, who established a small empire in regions of southern Syria and northern Jordan from the 4th century BCE, pioneered the small-scale production of such materials. They discovered the advantages of hydraulic lime with self-cementing properties by 700 BCE and utilized it to build masonry houses, concrete floors, and underground cisterns. The use of concrete was expanded during the Classical era. Ancient Egyptians and later Roman builders found that adding volcanic ash to the mix enabled the concrete to set underwater. The royal palace of Tiryns, Greece, dating back to 1400 to 1200 BCE, featured concrete floors. The Assyrian Jerwan aqueduct, made in 688 BCE, utilized waterproof concrete. Romans extensively used concrete from 300 BCE to 476 CE. Roman concrete, or opus cementitium, was composed of quicklime, pozzolana, and an aggregate of pumice. Its widespread use in Roman structures, such as the Colosseum and the Pantheon, freed Roman construction from the limitations of stone and brick materials, enabling new designs of greater structural complexity and size. Roman concrete was unique, as it hardened into a rigid mass when laid in the form of arches, vaults, and domes. Modern tests show that opus cementitium had similar compressive strength as modern Portland cement concrete, but its tensile strength was significantly lower due to the absence of reinforcement. The long-term durability of Roman concrete structures has been attributed to its use of pyroclastic, volcanic rock and ash. These materials react with seawater to form altobermorite crystals over time, which help give the concrete a greater degree of fracture resistance. Consequently, many Roman structures using concrete, such as the Baths of Caracalla in Rome and the Pont de Garde in southern France, still survive to this day. Another important innovation that helped in improving structure and tool-building techniques that developed in this time was the emergence of metallurgy, particularly iron smelting. Smelting, the process of extracting usable metal from oxidized iron ores, is significantly more challenging than tin and copper smelting due to the requirement of specially designed furnaces for hot working. Despite iron being a common impurity in copper ores, humans only mastered iron smelting several millennia after they mastered bronze metallurgy. The exact origin of iron smelting is not conclusively known. Archaeological evidence suggests the Middle East as a potential origin, with wrought iron artifacts surfacing during the Bronze Age in the 3rd millennium BCE. The widespread replacement of bronze weapons and tools with those of iron and steel defines the Iron Age, with the transition happening at different times across various regions. Iron became dominant in many regions including Mesopotamia, Egypt, India, Central Europe, and China. Notably, around 500 BCE, Nubians became significant manufacturers and exporters of iron, having learned the use of iron from the Assyrians. One of the earliest smelted iron artifacts, a dagger with an iron blade, was found in a Hattic tomb in Anatolia. Notably, iron objects found in the tomb of Egyptian ruler Tutankhamun also included meteoric iron artifacts. Iron was initially smelted in bloomeries, which produced wrought iron, a malleable but relatively soft alloy. Various theories exist about the origin of iron smelting. Traditional views credit the Hittites of Anatolia, but this theory has lost mainstream acceptance due to lack of archaeological evidence. A more recent theory attributes the development of iron technology to disruptions in the copper and tin trade routes at the end of the Late Bronze Age. However, this theory lacks archaeological evidence suggesting a shortage of bronze or tin in the early Iron Age. Across the world, another civilization was growing and flourishing, and at the same time learning to harness the power of magnetism. The ancient Olmecs appeared to have the capabilities to use a type of compass to aid in their building and daily lives. The Olmec civilization, considered to be one of the earliest great civilizations in Mesoamerica, emerged in the tropical lowlands of south-central Mexico around 1500 BCE. Flourishing from about 1200 to 400 BCE, the Olmecs were among the first cultures in the Americas to develop a complex social structure and produce monumental architecture, sophisticated art, and a symbolic system of writing. Their influence can be seen in later civilizations throughout Mesoamerica, including the Maya and the Aztecs. Despite the limited amount of remaining artifacts and the destruction of many of their monumental structures, Olmec culture has been identified as an origin for many fundamental elements of Mesoamerican culture. One remarkable aspect of the Olmec civilization is the evidence suggesting they possessed a knowledge of magnetic properties and may have used this knowledge in developing a kind of compass. This artifact, often called the Olmec compass, refers to the possible use of magnetic lodestone, a naturally magnetized mineral, to establish cardinal directions. This compass predates the compass's commonly accepted discovery in ancient China by more than 1,000 years, highlighting the Olmec's technological and scientific achievements. The Olmec compass is a lodestone artifact that has been carved into a bar-shaped object with a pointed end. When the artifact is floated on water or suspended in the air, the pointed end aligns to magnetic north. The Olmec civilization used this knowledge for various purposes, including creating a more accurate layout of their cities and guiding their explorations. The use of magnetic fields for navigation indicates a high level of sophistication in understanding and manipulating natural phenomena. While it is important to note that there is still ongoing debate among archaeologists and researchers about the Olmec compass's precise function and the extent to which the Olmecs understood magnetic principles, its existence provides compelling evidence of the Olmecs' advanced technological and cultural development. The possibility that the Olmec civilization might have understood and utilized magnetic fields significantly earlier than other known civilizations is a testament to their intellectual and scientific prowess, reinforcing the importance of the Olmecs in the history of global technological development. Over this span of 2 millennia, human capabilities grew quickly in civilizations across the globe. It is astonishing how many of these discoveries and innovations are used today, from dice to concrete. As we end this discussion, man is poised to continue to accelerate his learning even further as he moves into the Common Era.
Learn anything at mathandscience.com.